Hi everyone, and welcome to Gravity Wall Analysis with LimitState GEO, a step-by-step introduction. I'm Tom Pritchard, I'm Principal Engineer here at LimitState, and I'm your host for today. Our speaker will be Professor Colin Smith, the LimitState GEO Product Manager, and also an originator of the DLO technology that underpins the LimitState GEO software. Today's webinar will provide you with a step-by-step walkthrough of the modeling and analysis of a wall problem using LimitState GEO, and you'll learn about many of the important considerations you need to take into mind when setting up the model, as well as the benefits offered by the software in comparison to traditional analysis methods. If you have any questions at all during the webinar, then please feel free to ask them using the Q&A functionality that should be in the webinar interface, and we'll pick those up at the end of the session. There are a lot of attendees today, so we might not have time to get around to all of your questions during the webinar itself, but we will be sure to follow up via email afterwards. So without further ado, I'd like to pass you over to Colin.
Okay, thank you, Tom. So by way of introduction to the software, LimitState GEO is a fully general ultimate limit state analysis program designed to identify the critical collapse mechanism for any problem type in the form of a slipline mechanism. And this slide here gives you a flavor of the range of problems that you can solve with the software. Now, as Tom mentioned, in terms of the specific content today, we'll be looking at modeling a retaining wall, and specifically a cantilever T-wall that shares many characteristics with gravity walls in general, and some additional extra features which I'll be looking at in this webinar. As this is a short presentation, the main aim is to give you a flavor of what the software can do and how to set up a problem. And there won't be time to get into the details of all the software functionality. However, there will be time at the end for questions. So what problem are we going to look at? We're going to look at a 5 meter high reinforced cantilever T-wall, backfilled with granular material, subject to a surface surcharge of 10 kilonewtons per meter squared. It's adjacent to a stratum of stiff clay and founded on a stratum of loose sand. We have the model geometry available as a DXF file, and we want to look at both internal and external failure. So global failure, but also failure that may involve the wall itself. Excuse me. So the model, as I've said, will be available as a DXF file. The soil properties we're going to use are as follows in this table. So a granular backfill is going to be a drained material. In the software, we have the option to define materials as either always drained, that will generally be granular material, undrained materials, or materials that can be both drained and undrained, depending on whether you're doing a long-term or a short-term analysis. And those would include clay-type soils. So here you can see for the granular backfill, we're going to use a C' of 0 and a phi' of 32 degrees. The loose sand, we're going to use a built-in default material with a 30-degree angle of friction. A stiff clay as a default built-in material with an undrained shear strength of 120 kilonewtons per meter squared. For the wall, we're going to model as a rigid material, and later on we'll look at how we can model wall failure. Now, typically, when you shear on a wall interface, you get a lower resistance than in the soil itself. So here the soil wall properties are going to be taken as 2/3 of the adjacent soil material. So for example, the loose sand, which has an angle of friction of 30 degrees, we're going to take the interface friction of that material with the wall as 20 degrees, 2/3 of 30. And since this property only exists on the interface, unit weights are not relevant, so we're just going to set those as 0. So we will now build the model from the DXF file and add in the soil properties and boundary conditions. So we'll just pull up the LimitState GEO software. So this is the screen you get when you open it with no file. And I'm just going to go through the sequence of commands. So we'll first use the file import function and import a geometry, which is a DXF file. So I've got that one already set up. we have some options to manipulate the geometry. Initially, we're just going to accept the defaults, and this is the geometry we get. And if I right-click with the mouse, I can clear all the construction lines, which get rid of those, and that leaves me with the core geometry. So we now need to define our soil properties and assign them to the model. So to create a material, I can use this function tools create new material. I have a choice of types of material. Here I'm using a more cooler material, and I'm first going to generate the granular backfill. I can choose any color I like for it, so I'm going to pick this color. Because it's granular, it's always going to be drained, whether it's a long or short-term analysis. And we've got a friction angle of 32, dry unit weight of 19.5, and a saturated unit weight of 21. So we click OK, and we've got that material now appears in this Materials Explorer on the left-hand side of the screen. And I can assign that to the problem. I can drag and drop it, so I can drop it into this zone and this zone, which are intended to be the backfill zones. I can create a wall material now. So again, create new material. This time we're going to use a rigid material. That means it won't deform. So call that wall. Give it a color gray. And it's going to be concrete, so we'll give it a unit weight of 24. Click OK. So that again appears up here in our Materials Explorer. And again, I can drag and drop that into the relevant parts. Now the wall has been subdivided. We'll look at later why that is. So that's our wall. I said we're going to use some built-in materials for the other soils. So we're going to use a stiff clay, this built-in material. Anything I click on in the Materials Explorer on the left, its properties appear on the right in the property editor. And you can see it's got this undrained strength of 120. So I'm going to drag that over and put that there. And then we're also using a loose sand. That's this one. Again, it's got an angle of friction of 30, which is what we wanted. That's going to underlie the wall, and also we'll use that as the material in front of the wall. So that's created our soil properties. We then need to create our interface materials. So again, very quickly, we'll just create new material. This is going to be a more cooler material. Okay, so create interface. I'll leave that as green. This again is going to be always drained, and it has an angle of friction of 21.4. And the unit weight doesn't really matter. We're only using it on boundaries, but we'll just set those to 0. And that needs to go between the backfill and the wall. So rather, we can drag and drop this if we want onto the interface, the boundary there. And you see that goes green, so that gives us the interface. Or we can assign materials a different way. If I click, oh, just a moment, I seem to have got the wrong setting here. Yeah, if I click on the boundary, I can select multiple boundaries, and then their properties, common properties, appear in the property editor on the right. I see this material, it says 0 materials assigned. If I click in this box and click change, I get a list of materials that I can assign, and I'm going to click that one. And now that gives me that material on those interfaces. I'll then create the side wall interface. Give a slightly different color. And that one again is always drained and has an angle of friction of 20. It's already there. And the unit weight is 0. and that needs to go everywhere the wall is adjacent to the soil. I'll just do this in 2 stages. So we're going to use the loose sand wall interface material, so you can see that's assigned that there. And again, assign it to these. That's it. Okay. So we've now assigned all our materials. We had a surface surcharge. So up here, again, if I click on the boundary, I can see in the property editor, I get loads. I want a variable load, a normal load of 10. And I want that to be an unfavorable load because we think that's more likely to cause collapse. This setting is used when in conjunction with partial factors such as Eurocode 7. And we also want a surcharge on this boundary as well. So we put 10 here. And also unfavorable. That's got our surcharge on. And then to complete the model, we need some other boundary conditions. So at the edges, we are going to have fixed boundaries. So again, I can do this all in multiple select, fixed boundary there. And if I click the buttons up here, I can resume back. If I use the mouse, I can zoom in on the model and I'll set these to fixed. So that's our model almost completely set up. We'll come back to nodal density, but I'm going to set this to fine. This controls the kind of accuracy of the solution. So we'll set that to fine, and then I'm going to do one final thing. We have a scenario manager. What I would like to do is solve this using Eurocode 7 partial factors. And these are built in, so I can pick design approach 1 combination 2 here. We'll look at that first, and this will assign partial factors on loads as shown here, and primarily factor down on material properties strength. And we can ask this to do a long or a short-term analysis. Here I'm going to do a short-term analysis. That means we'll use the undrained shear strength of the clay, but the granular material will just use its frictional strength regardless of whether it's a long or short-term analysis. So that's us fully set up. We're ready to do our analysis. I'll just save that file. And we'll just quickly hop back to the presentation. So in terms of analysis, before we do the analysis, just a little bit of background about how the software works. So in order to generate these slipline solutions, it uses a procedure called discontinuity layout optimization, which is a rapid and direct means of analyzing the collapse state. Came out of some EPSRC funded research at the University of Sheffield and was published, core publication was back in 2007 in the Proceedings of the Royal Society. We can describe the process pretty straightforwardly. First of all, we have a problem domain, which is here is a rectangular block of soil with a surface load and supports to the left and the base. Instead of discretizing it into elements, we populate the domain with nodes. So here we've got a 4x3, 12 nodes. We connect every node to every other node with a potential slip line. So that's 12 times 11 over 2, 66 possible lines. And then we use optimization to pick out of those the slip lines that give a mechanism that dissipates the least energy. And that's the one that's going to be critical. This problem, we've got 12 nodes. Typically, we'll be using 1,000, 2,000 nodes and millions of potential slip lines to solve. And this gives us a really flexible way of generating slipline mechanisms. Just illustrate one example here in terms of a foundation. We can very rapidly get to the classic pyramidal mechanism here. And one of the nice things about this method is that for ultimate limit states, your slipline problems typically often contain singularities where you get many slip lines meeting at a point. And this is handled inherently and without difficulty by the method whereas finite elements methods can struggle here and require element refinement techniques and so on. Okay, so that that's a quick recap on how the software works. We'll now jump back to the software and actually solve. So to set that process in motion, we simply click the solve button here up at the left. And what it should show, you can see all the nodes there, the black dots, and it quickly goes through this optimization and finds the critical collapse mechanism. So in this case, it's finding that we're getting a sliding failure with design approach 1 combination 2, and we're getting wedges in the backfill and the loose sand in front. And we get a solution 1.92. So just explain what this actually means. So when we're doing ultimate limit state analysis, everything that we design should be stable, and we need to do something to destabilize it. Either we're going to have to increase a load somewhere in the system to fail it, or reduce the strength of the materials in the system to fail it. In this particular example, I've chosen to increase a load and in fact just increase the surface surcharge. So if I click on this solution, it tells me that the loads on boundaries 17 and 29, and if I click on these, they'll actually get highlighted. You can see that boundary 17 is this here, and boundary 29 is this one here. It's saying if that is increased by a factor of 1.92, then we will get collapse. And in the table, you can see the characteristic value. The design value is a design approach 1 combination 2 factored 1.3 times 10. And then we have to multiply that by a further 1.9 to get collapse. So essentially what that means is that this complies with the code because we have to increase the load beyond its current value in order to get to collapse. So any value bigger than 1 is typically means we've complied with the code. Okay, so that's an initial analysis looking at a kind of global failure. So now we're going to look at how we model structural failure. So if we want to model structural failure in a stem wall, we might expect it at one of 4 locations. So on the right here, you can see the 4 positions where this might occur. And for bending failure in this wall, we can model it using rectangular stress blocks. So a plastic hinge, sort of classic plastic hinge theory, would give us 2 stress blocks. And this can be modeled in the software using what's called a cutoff material. And all we do is we set the cutoff material that models yield in tension and compression to represent those stress blocks or those limits on those stress blocks. And they can be converted to the plastic moment of resistance using this formula sigma y BD squared over 4, which is for a beam. In our problem, we're doing a plane strain 2-dimensional analysis, so our width B is effectively infinite, or in this calculation, we're doing it per unit width into the diagram, so we can set that to 1. So in the table below, we've got the bending resistance in the 4th column. That's what we're aiming for, and the section depth in the 5th column. Combining those two using that formula, we can back calculate what the yield stress would need to be, and these are the values we're going to put in the software. So we'll jump back to the software and create that. So again, create a new material. So we're going to have stem bending. This time we're going to use this cutoff material. I'll give it a different color. And we have to give it a limiting tensile and compressive strength. And we decided those were going to be 5,000. So this new material here, I can drag and drop that onto these locations, and essentially that will allow the software to model bending at those locations. And for the toe and heel, again, I can model and for those values, we I think the values of 3,000 that we were going to use, reflecting the slightly thinner section. So those, again, we can drag and drop them onto these locations. And that will now allow the software to model bending in the particular one. Now, if I preview nodes here, you can see the nodes that we've used in the problem. So the software will connect every node to every other node looking for potential slip lines. However, it's useful to have more nodes along these hinge locations so that we can better represent that kind of two hinge block process. So on these interfaces, I'm going to increase the nodal density from half to a spacing of 0.1. And if I preview the nodes again, you can see I have many more nodes there, which will allow me to model the rectangular stress blocks more precisely. Okay. So we'll just quickly jump back to the presentation. I won't go into this, but if we want, we could also model the possibility of shear failure through the wall by introducing a shear material on those interfaces and looking at the allowing the software to model shear as well. So we get what are called combined materials, where we've got both a shear material and a bending material on the same interface. We won't do that. We'll just go straight to looking at the failure mode. So again, if we pull up the software here, I'll just click solve. And this time you can see that the software has identified that we can fail the wall by bending at this particular point. We've got a lower adequacy factor than we had before. Again, clicking on that, it's just saying the surface surcharge needs to reach this value to cause collapse. And if we zoom in here and I click here, you can see these rectangular stress blocks. And if I hover over them, you can see we're getting minus 5,000 here and plus 5,000 here. Excuse me, which is giving us that bending strength, that plastic yield. So that allows us to do that. We can also introduce the other Eurocode partial factors here. I can click on multiple scenarios here and get the software to model more than one. I'm going to pick DA11 here. Now, DA11 effectively factors up actions, doesn't factor material properties, and it's not always clear which action it is that is to be factored in the problem. One could choose a number of forces or actions in the problem. It could be the weight of the backfill. It could be the active pressure on the wall. It could be an internal structural force. A common assumption is to factor up the active pressure on the wall. This is quite challenging to do in any numerical model. And in fact, the new forthcoming version of Eurocode 7 addresses this. But since we've got a cohesionless backfill, we get the same effect by factoring up the weight of the backfill material itself. So what I'm going to do is select these two materials and state that they've got an unfavorable loading type, and that means that DA11 will factor those by 1.35, which in effect will factor up the active pressure by 1.35. It won't change the DA12 analysis because the unfavorable permanent factor is still 1. So we can now solve this problem and look at both design approaches. So what the software does is it looks at both analyses, one after the other. So DA12 still giving us 1.64, and DA11 it's giving us a factor of 1.8. So DA12 is still critical in this instance, and we still get this kind of failure mechanism. So that pretty well wraps up what I wanted to demonstrate today. We're kind of pretty much out of time, so we'll just wrap up with a brief summary, but hopefully that's given you a flavor of how to model problems like this and use partial factors. So we'll just jump to the summary. So hopefully you've seen that the workflow is pretty straightforward from geometry import, and we can generate reports. I didn't have time to look into that. Very intuitive user interface. You're in control. You can solve problems with one mouse click. Easy to handle partial factor application. Very interactive problem. We can play around with all the parameters in the geometry interactively to get a better feel for the problem. And we can solve any ULS problem type. For this wall problem, we did not have to try and solve or analyze separately a sliding failure, an overturning failure, a bearing failure. The software will always pick out the most critical one. And often the most critical one is a combination of the two, such as a combined bearing sliding kind of failure. And as you saw in one of the first slides, we can solve any problem type. So the software can be used to model a wide range of problem types such as this. Okay, I will wrap up there, and we've got a little bit of time for questions. So if you've posted questions, we can have a look at those. Okay, so we've got a question: how can we add water to this problem? So let's have a look. So there are various ways of adding water. Simplest one is to use the water table tool here. If I click on this button here, I can draw in a water table. So I'm just going to draw a horizontal water table in. And now that will model the effective water. So we should expect that to destabilize things because we're going to reduce the effective stresses, particularly in the underlying film. And if I click solve here, we'll see what happens. So our adequacy factor has dropped below 1 now. It's 0.52 for DA12 and 1.7 for DA11. So because we've dropped below 1, we don't comply with the code anymore. It means that the surface surcharge is now too big. In fact, in order to get collapse, we need to reduce it by a factor of roughly a half. So it's overloaded at the moment. And we can see that the critical mechanism has now changed. Because we've added water, it's actually made that sliding failure more favorable than the bending failure of the wall. Okay, we have a few more questions coming in. I'll try and answer as many as I can before we're out of time. Yeah, please send a link to the recording. We will provide a recording link after the webinar. Can we calculate deformations or deflection? This is ultimate limit state software, so it is designed to analyze the ultimate limit state, the collapse state. So it doesn't do serviceability limit state calculations or calculate deformations. So it's not able to do that. Can we model geogrids as basal reinforcement? So it is possible to model geogrids, and the software models those in the same way that most conventional analyses do. So yes, you should be able to use it as basal reinforcement, but it depends particularly on what mechanical reinforcement, that the particular analysis method that you're trying to adopt, or properties of the reinforcement. We can perhaps answer that question in more detail separately. can we add exclusion zones for loads? Yes, so I can quickly show that one. If I want to have the load over in a smaller area, I can use this vertex tool here on the left. I can add vertices to, failing to get that to click. Let me try again. Zoom in a bit more. Yeah, one there, and say another one there. And then I can remove the load. So if I wanted the load further back, I can take this one out. Then I can take this one out. And so now I've got a load acting over a smaller area. And again, I can analyze that, and we'll get a slightly different failure mode and a different load adequacy factor on that. But in that particular case, it still doesn't comply. Okay, I think that's all the questions we've got time to answer at this moment. So thank you very much for listening, and hope you found that useful. I'll just pass back to Tom to wrap up the webinar.
Thanks, Colin. So we've got just a few things to cover before the end of the webinar. Firstly, we do hope that you enjoyed the presentation and found it useful. As mentioned at the start, we'll answer any questions that we didn't manage to get around to in the Q&A in the upcoming day or so via email. Again, also mentioned by Colin, a recording of the webinar will be made available on our YouTube channel in the next day or so. An email will come out to tell you when that is available. And do also make sure to follow us on YouTube and on LinkedIn as well for all our latest news and upcoming events. And lastly, if you did want to try LimitState GEO for yourself, if you're not already a user, then be sure to head over to LimitState.com/geo to download a free trial. So that's it for today. We do look forward to welcoming you all at one of our future webinars. Take care, and we'll see you soon. Goodbye.